These notes are on operations on complex numbers. These notes are going to be fairly long, so you may need to kind of jump ahead and behind depending upon which concept was especially difficult for you. So the first thing that we're going to talk about is the complex plane. So you've seen a real plane. We have an x value and a y value. So we can also graph complex numbers by looking at the complex plane. So the first thing we want to do is we're going to talk about our real number. And our real numbers we can see on this lovely number line. Here are our real numbers. Now, it turns out that if I multiply 1 by -1, I get a 180 degree rotation. So 1 times -1 equals -1, and that yields a 180 degree rotation. Now, since we're talking about complex numbers, what happens when I multiply 1 times I squared? Well, that also equals -1, so I still have a 180 degree rotation. So I bounce from 180 degrees to -1. Which then, if I know that from here to here is 180, and that's I squared, it begs the question, well, where's I? So if I squared is a 180 degree rotation, we can conclude that I is a 90 degree rotation. So there's my real number line, and here at 90 degrees is my imaginary number line. So let's look at that in practice. So in essence, what ends up happening is our complex plane looks just like our coordinate plane, except that I have a real axis and I have an imaginary axis. And so each of the points that I'm going to plot exist with some real portion and some imaginary portion, and so they end up somewhere graphed on this two-dimensional image. So point A has a real portion that's -1, so I'm going to move along my real axis, -1. But then it has an imaginary portion that's 5, so that means I'm going to go up 5. There's my A. B has only a real portion, so I'm only going to go on my real axis, and that real portion is simply 2. C has only an imaginary portion, so I'm only going to go on my imaginary axis, and that is at -3i. D, again, I have both portions. I have a real portion that's -4 and an imaginary portion that's -2. And E, I have a real portion that's +2 and an imaginary portion that's +3. And I have now graphed these 5 points on the imaginary plane. The next part of my notes is going to be adding complex numbers in the complex plane. This is going to connect back to a topic you did in Math 1, dealing with vectors. So the first thing I'm going to do here is I'm going to add this as if I don't have a complex plane. It'll make it a little easier. So I know that when I'm adding these, I'm combining the like terms essentially. So I have -1 plus 2 is +1, +5i plus -3i is +2i. Graphically, when I'm using the complex plane, I'm going to treat these as if they're vectors. So my first vector is at -1, +5. So there's my first vector. Sorry about that. Not so easy to make a straight line sideways. And then I follow the instructions of the second vector. From here, I add this vector. So from here, I go 2 over along the real axis, and 3 down along the imaginary axis. And in order to get my final answer, sorry, I'm just going to white this out a little bit so it's a little easier to see. Again, I apologize for my less than straight line. So my final answer is where I started to where I ended, which is the point 1, 2, which is indeed the complex number 1 plus 2i. The next portion of our notes is called the module of a complex number. The modulus. Typo there. The modulus of a complex number. A modulus is the magnitude or length of the complex number as a vector in the complex plane. And we denote that as using absolute values around it. Remember absolute value? So absolute value means distance from 0 or the origin. So when I'm finding the modulus of a complex number, I'm actually asking for how far is that number from the origin in the complex plane. So when I'm looking at this, the first thing I'm going to do is I'm going to graph this complex number. So 4 on the real axis, down 2 on the imaginary axis. So the modulus, the absolute value, means I want to find this length right here. Well, we know from experience that I can very often, when given a line through the origin or any line in the real plane or complex plane, I can create a triangle. So I'm going to do that right here. I'm going to create a right triangle. Well, the nice thing about a right triangle here is that I know this length right here, it's 4. And I know this length right here, it's 2, which means using Pythagorean theorem, I can find this length. So we'll call this x, and we'll say that 4 squared plus 2 squared equals x squared. So 4 squared is 16 plus 2 squared is 4 equals x squared. So I end up with 20 equals x squared. Square root of 20 equals x, but I can simplify the square root of 20 to be 2 root 5, which means this length is 2 root 5. That's what this is asking. What is that length? So that length equals 2 root 5. The next operation that I can work with when I am working with complex numbers is something called the complex conjugate. And the complex conjugate plays an interesting role when we're looking at the roots of quadratic equations. So the first thing is that the complex conjugate all it does is change the sign of the imaginary portion of our complex number. And we denote it by putting a bar over it. So the complex conjugate of 4 plus 2i is 4 minus 2i. And the complex conjugate of negative 8 minus 3i is negative 8 plus 3i. Again, the sign in front of the real portion of the complex number does not change. It's the imaginary portion that changes sign. So now let's look at what happens when I do some adding or multiplying of the complex number conjugates and its number. So we're going to rewrite this. Remember, that means a minus bi. And then I still have plus a plus bi. And a negative bi and a positive bi cancel, so I'm left with 2a. So that's kind of an interesting thing, that having a complex conjugate and a complex number, when you add them together, they get rid of the imaginary portion. Let's look at multiplying. So multiplying, again, I'm going to have a minus bi times a plus bi. I'm going to do my double distribution. So I've got a squared plus abi distribution minus abi plus, minus b squared I squared minus b squared I squared. My middle terms cancel, they're the same sign. And I end up with, remember, I squared is -1, so I end up with a squared plus b squared. So by multiplying a complex number and its conjugate, I end up again with no imaginary portions. So a complex number and its conjugate, adding them or multiplying them, give us real numbers, which is a very interesting relationship that we have there. The last thing I want to say about complex conjugates is that when I have a quadratic equation that has complex roots, they always come in twos. And they always come as the complex number and its conjugate. So quadratic formulas with complex roots always come in the pattern of x equaling a plus bi and x equaling a minus bi. Complex roots are always going to come in this pattern. So thus far we have done adding and subtracting, multiplying complex numbers. So now we're going to look at dividing complex numbers. So we can't divide by a complex number. There's no actual way of doing that. But we can multiply a complex division problem by 1, and we want to multiply it by a very strategic one. Remember what we just did a second ago, where we found that a complex number and its conjugate, when they multiply, become a real number? So I can divide by a real number. So what I'm going to do here is I want to turn the denominator into a real number. But I don't want to change the value of my number. So the only way to do that is to take my complex number being divided by a complex number and multiply it by 1. And the one I'm going to choose here is the conjugate of the denominator. So remember, c minus di over c minus di is 1. I'm not actually changing the value. I am simply dressing it up. I'm turning 1/2 into 2/4 into -5 over -10. It's not changing the value. It's just making it look different. And remember from the work we just did a few minutes ago that I know what this is going to simplify to be. It's going to simplify to be c squared plus d squared. That's what a complex number and its conjugate multiply to be. So now I'm left with multiplying the numerator. So I'm doing my double distribution, so a times c, a times di, b times c, and b times di, bi times -di, which gets me negative b di squared, which we can simplify a little bit here. So I have ac minus adi plus bci plus bd over c squared plus d squared. So I then can rewrite this as having a real part, ac plus bd, all over c squared plus d squared, and an imaginary part, negative adi plus bci over c squared plus d squared. Combine the like terms and put it over the entire denominator. Combine the like terms, put it over the common denominator. So now let's look at an example of this. So actually, I just want to note here that a plus bi over c plus di is the same thing as a complex number. Complex number being having a real portion and an imaginary portion. So by multiplying by 1, and remember this is 1, which is why I didn't write it again, I have written this number, which was a complex over a complex, as just a complex number, which is what I wanted. So let's look at an example. Again, I want to be very strategic about this fraction. I want to keep it the same value, but I want my denominator to be real. So I get that real by multiplying by its conjugate. In my numerator, I do my double distribution, 3 times 4, 3 times 2i, 5i times 4, and 5i times 2i. In my denominator, my pattern is always going to be my a squared plus my, use parentheses, and my b squared, either the positive or the negative. Either way, squaring a negative is positive, squaring a positive is positive. So I've got 12, and I know that my negative 10i squared is positive 10, plus 14i, all over 16 plus 4. I get 22 over 20, plus 14i over 20, which means if I reduce this, I end up with 11 over 10, plus 7i over 10. Real part, imaginary part, a complex number. This is a complex number divided by a complex number. I want a complex number, and so this is the process I use in order to do that. Let's look at a second example, because these problems are a bit, can be initially a bit difficult. So my second example, I have 7 minus 3i divided by negative 2 minus I. Again, I want to multiply by 1, but I'm picking my 1 strategically so that I end up with my denominator being a real number. So the complex number and its conjugate. Double distribution, 7 times negative 2, 7 times I, negative 3i times 2, and negative 3i times I, all over my a squared plus my b squared. Remember, it's bi, so my b is the coefficient of what's in front of the I. 1 or negative 1, again, squaring it's not going to change that. So now I have in the numerator negative 14 plus 3 plus 13i, all over 4 plus 1. So I have negative 11 over 5 plus 13i over 5. So I've taken my complex number divided by a complex number and rewritten it as a complex number. The next example is finding the distance between two complex numbers. So finding the distance between two complex numbers, I'm going to do a quick sketch here. So I have over 4 up 1, and my other complex number is over negative 1 down 2, and I'm trying to find this distance right here. Well, remember, when I'm finding distance, I'm really talking about Pythagorean theorem. So I'm going to kind of sketch in my right triangle right here. And my right triangle, this is my change in y's. So when I'm looking for the distance, my distance squared is going to be my change in y's squared plus my change in x's squared. My change in x's, that's this length. So my change in y's right here is 3. And I can get that by saying, hey, look, this is 1 minus negative 2. Change means difference. My change in my x's is 5. And again, that's my real minus my real. Distance, change in means subtract. So I get d squared equals 3 squared plus 5 squared. D squared equals 9 plus 25. D squared equals 34. So the distance is the square root of 34. The last part of these notes is finding the average. The average of two complex numbers is going to be the average of the imaginary parts plus the average of the real parts. So I have 1 plus 5 divided by 2 plus 4i minus 2i divided by 2, which equals 6 divided by 2 plus 2i divided by 2, which is 3 plus I. So the average of these two complex numbers is the complex number 3 plus I.